Welcome back. We are still continuing with the current electricity topic, and this is part 6B. Part 6B, the domestic electricity supply, the second part. I am still your host, Amanda Dennis of Seroma Christian High School. Now here, we are going to explore the cost of electricity, the electricity bills that we always get, how they calculate them. So the commercial unit of electricity is what we call the kilowatt hour, abbreviated as kWh. Small k, not capital K but small k, kWh. The W has to be a capital and then small h. Kilowatt hour. The kilowatt hour is used by electricity boards, now like Umeme in Uganda, as the unit to present the amount of electrical energy used. So let's get a definition of a kilowatt hour. The kilowatt hour is defined as electrical energy consumed at a rate of 1 kilowatt for 1 hour. As simple as that. The electrical energy consumed at a rate of 1 kilowatt, or you can say at a rate of 1 kilojoule per second for 1 hour. So 1 unit of electricity is what we call 1 kilowatt hour, and if you want to convert this energy to joules, convert this a kilowatt, so convert this to watts. That will be 1000 watts, and convert this 1 hour to seconds. That's 3600 seconds. And when you multiply 1000 times 3600, you end up with 3.6 m, which is 3,600,000 joules. Therefore 1 kilowatt hour is equal to 3,600,000 joules. 600,000 joules, sorry. I repeat, 1 kilowatt hour is equal to 3,600,000 joules. In calculations of the cost of electrical energy, the following should be noted. Please note this. Number 1, the total power should be in kilowatts. We are dealing with kilowatt hours as the unit, so the total power should be in kilowatts. Number 2, the total time should be expressed in hours. Total time has to be in hours, and the cost per unit, or what we call the unit cost, which is the cost per kilowatt hour, should be known. Like currently, for Umeme, they are currently charging around the for the home use. We always find it's around the 825 to 800 and maybe and 50 around. Then for big companies, they reduce. For the factories, the cost is a little lower. Now, note these two formulae. The number of kilowatt hours, or what we call the number of units, has a special formula. How do you get it? Remember, you want to get kilowatt hours. Kilowatts, this is power, and if you talk about kilowatts, it means you're talking about power. And this hour, it means you're talking about time. So how do you get the number of kilowatt hours, or how do you get the number of units? The equation should be easy for you to get. Kilowatt will be this will be representing power, and this represents the time. So we get total power in kilowatts, total power in kilowatts times time in hours. That is a formula that should never thinking about forgetting, please. Number 2, how do you get the total cost? The bill. Total cost is equal to the number of units times the unit cost. So these two formulae, the first one, number of kilowatt hours, or the number of units, is equal to the total power in kilowatts times the time in hours. And this other second one, the total cost, is equal to the number of units times the unit cost. These two formulae are very important. Please don't forget them. Thank you. Okay. I should give you an example. Number 1, find the cost of running 60 watts bulbs, 560 watts bulbs for 8 hours if 1 unit costs 400 shillings. So remember, there are 5 bulbs, each one has a power, it's rated 60 watts and it's operating for 8 hours. So each unit costs 400 shillings. What are you supposed to do? Get the total power in kilowatts. So we are given the power here as 60 watts. So convert to kilowatts by dividing by 1000. Then remember there are 5 bulbs. So you multiply by 5. You're going to end up with 0.3 kilowatts. So we have our power in kilowatts. So the number of kilowatts or kilowatt hours is equal to the total power in kilowatts times the time in hours. So if you want to get the number of units, just get the total power in kilowatts times the time in hours, which is going to be, we have 0.3 kilowatts, then multiply by the 8 hours. Remember, they told us that they're operating for 8 hours. And so we end up with 2.4 kilowatt hours, or you can say 2.4 units. Now, the total cost therefore becomes the number of units, which is 2.4, times the unit cost, and we get 960 shillings. That will be the amount of money that you will pay. Let's look at another example. Example number 2. Find the cost of running 5 60 watts lamps and 4 100 watts lamps for 5 hours each day for 10 days if the electrical energy costs 250 shillings per unit. Look at this. Now, these are lamps, but they have different ratings and they're operating for the same time. Remember, the number of units is equal to the, basically, total power in watts, kilowatts. You put the total power in kilowatts times the time in hours. So, let's start with, that's our formula. Number of units is equal to total power in kilowatts times time in hours. Let's start with the 60 watts lamps. The number of units will be, so get this power, which is 60, put it in kilowatts. So you get 60 over 1000. Remember, there are 5 of them. 5 bulbs, 5 lamps. And they are operating for 5 hours each day for 10 days. So this is the total time in hours. And this is the total power in kilowatts. And what does that give us? 15 kilowatts. 15 kilowatt hours. Or you can say 15 units. Therefore, the cost for running the 60 watts lamps, 5 of them, is going to be 15, which is the number of kilowatt hours, or the number of units, times the unit cost, which is 250. And we get 3,750 shillings. So for the 100 watts lamps, we are having the number of units will be equal to, remember there were 4, and each one was rated 100 watts. So convert the 100 watts to kilowatts by dividing by 1000. Then times the 4, because there are 4 lamps. This is the total power in kilowatts. Then times the number of hours. For the 10 days, each day they are working for 5 hours. So you end up with 20 kilowatt hours, or 20 units. And here also the cost is going to be 20 times 250, which gives us 5,000 shillings. Therefore, the total cost becomes 3,750 plus 5,000, which will give you 8,750 shillings. That will be the bill that the Umeme man will hand you at the end of the month, or at the end of the 10 days. Actually, this is not for the whole month, it's for the 10 days. Okay, number 3. What is the cost of using 5 lamps of 100 watts each for 2 hours every day for 1 week if the cost of 1 unit is 90 shillings? Oh my God, I wish there is such a country. Okay, 90 shillings, maybe for Kenya. For Uganda, this is impossible. What is the cost of using 5 lamps of 100 watts each for 2 hours every day for 1 week if the cost of 1 unit is 90 shillings? Number of units will be equal to total power in kilowatts times the time in hours. By the way, don't get me wrong. Don't quote me wrongly. it's not realistic for us in this country to have a unit cost of 90 shillings. The cost of production is high. Cost of production of that power is high. Yes, you have to bear that in mind. We shall look at the production of electricity later on. So back to our formula, number of units is equal to total power in kilowatts times time in hours. And now the total power in kilowatts will be, each lamp is rated 100 watts. Therefore, convert that to kilowatts by dividing by 1000. So you get, this is number of this is kilowatts. Remember, there are 5 of them, so times 5, so you get a total power times, they are saying, times the time in hours. They are operating 2 hours each day for 1 week. That means the total number of hours will be 14. So you multiply 2 times 7 anyway. And so we get 7 kilowatt hours as the number of units. The cost is equal to number of units times cost per unit. You know that, which becomes 7 times 90, and we get 630 shillings. Okay, I have number 4 here. What is the cost of using 3 kettles of 800 watts each, a flat iron of 1000 watts, 3 bulbs of 60 watts each, if they are used for 3 hours every day for 30 days? And you're told that each unit costs 100 shillings. Look at this. This can be a very good number in case you find it, because it's just very easy. Use the formula, number of units or number of kilowatt hours is equal to power in kilowatts times time in hours. So let's go slowly. We have kettles and there are 3 of them. Number of units will be, the total power is going to be, remember there are 3, times the power for each one of them in kilowatts. You get this. This is 800 watts, so you get 800 divided by 1000. Then times the total time for which they work. Remember, total time the time has to be in hours. We are given here that they are working 3 hours every day. That means 3 times for the 30 days in a month. The 30 days. So we shall end up with 216 units used for the kettles alone. So the cost for the kettles is going to be the unit cost, which is 100, times the number of units, so you end up with 21,600 shillings. Okay, let's also look at now the flat iron. The flat irons, actually there are many, not just one. The number of units, remember, the flat iron was rated what? Flat iron of 1000 watts. 1000 watts. So if it's rated 1000 watts, that means that's 1 kilowatt anyway. Get this power times the total time. So remember, there are 3 hours each day for the 30 days. So you end up with 90 units. And the cost here will be 90 times 100, you get 9,000. For the bulbs, there are 3 bulbs. Each is rated 60 watts. Convert the 60 watts to kilowatts by dividing by 1000 times the total time in hours, and you get this. Please, you are free to pause and go back and watch this video again so that you understand these calculations. Actually, you can even go back and calculate on your own and compare with these answers and see whether you end up with the same results. So the cost of running the bulbs is going to be the units 16.2 times the unit cost, which is 100, and you end up with 1,620 shillings. So the total cost will be the cost of running the kettles, 21,600 shillings plus 9,000 for the flat iron, and then plus for the bulbs, which is 1,620. So we shall have a total bill of 32,220 shillings handed to us at the end of the month. Number 5, an electric kettle is marked 1.5 kilowatts containing 4 kilograms of water at 30 degrees Celsius. Now mark this. This is an interesting one. How long does it take to reach a boiling point? So if you're using this kettle, how long does it take for the water to boil? What is the cost if each unit costs 95 shillings? Given that the specific heat capacity of water is 4,200 joules per kilogram per Kelvin. Okay, now this is a very interesting question and I want you to treat it carefully. Remember, here we're just having energy conversion. For the electric kettle, we are having energy being converted. Here we have electrical energy being converted. So you have electrical energy turning into heat energy. Now remember, if you are given power here, power and asking for how long, so electrical energy basically is power times time. You get the power, which is power, we shall have power times time, should be equal to the heat energy. How do we get heat energy? If you remember, for the topic of heat, we already discussed that. The quantity of heat is equal to, you get the mass times specific capacity times the change in the temperature. So the power is 1.5. Now we can use this as, we can use watts. So we are going to remember, you have, if this is a standard calculation here, because now the heat, you're going to express it, this is given in joules per kilogram per Kelvin. Therefore here we have to use the SI unit, and the SI unit of power is the watt, so, or joules per second. So we can have 1.5 times 1000, that's the number of watts, times the time which they're asking for, should be equal to the mass, they gave us 4 kilograms, times specific capacity, which was 4200, times, now what will be the temperature change for the water to boil? It was at 30 degrees Celsius. Remember, water boils at 100 degrees Celsius, so the temperature change there is 70. You don't need to convert to Kelvin because the difference still remains the same. And from this formula here, from this equation here, you can get the value of T, which shows you how long it takes for the water to boil. Okay, now let me show you in a better organized way. We are saying water boils at 100 degrees Celsius, and electrical energy supplied is equal to the heat required to heat water up from, that T shouldn't be there. Now T, this T here, I'm not seeing you. From 30 degrees Celsius, it's supposed to be 30 degrees Celsius to 100 degrees Celsius. Please forgive me for that. So the power for electrical energy, its power times time, should be equal to MC delta theta. I've explained that. And you're going to end up with T is equal to 784 seconds. Those are the seconds. You can convert that to minutes or to hours, no problem. Now, let's look at part B. Part B says, part B said, what is the cost if each unit costs 95 shillings? So that means you have to calculate the number of units. Number of units. How do we get the number of units? Remember our formula? We say the number of units is equal to the power in kilowatts times time in hours. The power is 1.5. The time in hours, you get this divide. We had 784 seconds. So to convert to hours, you divide by the number of seconds in 1 hour, which is 3600 seconds. And we end up with 0.3267 units. So the cost will be the number of units times the amount, the unit cost, which will be 31 shillings. Number 6, Dennis paid an electric bill of shillings 180 after using 2 identical bulbs for 2 hours. Every day for 10 days at a cost of 60 shillings per unit. This is supposed to be every day for 10 days at a cost of 60 shillings per unit. Determine the power consumption for each of the bulbs. So can you get the power rating? Yeah, if you remember what we said, you can say let the power be let the power consumed be X. So let each bulb actually be rated X kilowatts. So we can say the number of units, remember from our formula, is equal to power in kilowatts times time in hours. And now there are two bulbs. Each one, its power is X kilowatts. So we are saying 2 times X. Then this is the total power in kilowatts times time in hours. They're operating 2 hours each day for 10 days. And so we end up with the number of units as 40x. But remember, the cost is equal to number of units times unit cost. So we end up, if you multiply 40x times 60, you end up with the 2400x. But remember, they told us that that cost was 180 shillings. So we end up with x is equal to 0.075 kilowatts, which you can convert, this one you can convert to watts, which is 75 watts. That means each bulb is rated 75 watts. An exercise. Ooh, this is for you. Please ensure that you always do these numbers. You pause, you do the numbers, and then you submit your work for marking to my WhatsApp number. Number 1, find the cost of using 2 100 watts bulbs and 3 60 watts bulbs for 8 hours. If the cost per unit is shillings 1, this is supposed to be 150. 150, please rewrite this. Let's change and say if the cost per unit is shillings, let's use the current shillings 830. Yeah, for example, for Uganda right now, 830. Don't use this, please. Don't think about it. Number 2, what is the cost of using 2 cookers, each of 2 kilowatts, 2 bulbs of 40 watts each, and 3 bulbs of 75 watts each for 5 hours every day for a month of 30 days if each unit costs 115 shillings. Yeah, those are your questions. Now, here comes something very interesting, the distribution of electricity. Yeah, we want to see how electricity flows. Distribution of electricity. The provision of electricity for public use is done in 3 stages. Remember, for electricity to reach you, these are the stages. Number 1, it's generated. Number 2, it's transmitted. And number 3, it's distributed to the homes, to the factories, to the different places. So a grid or a grid system is the transmission and distribution network of cables. So when we talk about a grid or the grid system of electricity, we are talking about the transmission and distribution network of cables. That's what we call the grid. I'll show you a few pics, a few images of the grid. I think you have seen the pylons, you have seen those poles that are carrying the electricity. So the network of cables for the transmission and distribution is what we call the grid. So the grid system for a single phase is what we're going to deal with, and the two wire 240 volts single phase grid system is a distribution network of cables used to deliver electricity to consumers with small loads such as households. In this system, electrical energy is supplied to the installation of the consumer's house via a twin cable, or what we call a 2 single core cable. Such a cable has one conductor or that wire connected to the positive, which is a live wire of the supply, and another conductor, which is a wire connected to the negative or the neutral wire. The neutral wire is earthed at the supply end. All fuses and single pole control devices, e.g. switches, circuit breakers, and thermostats, are connected in the live side, the live wire, only, since there is no need for any break in the neutral. And the wiring in the consumer's house is insulated and connected to these two wires or leads. Remember, when you say the two wires, we're talking about the live and the neutral, or the earth. And enclosed in a metal casing or in a conduit. If a metal casing is used, then it should be earthed to prevent it from becoming live in case the insulation breaks, and also to earth appliances. We talked about this earlier on in part A of this very subsection. In the house wiring, the leads from the mains are covered with red insulations, while those connected to the earth or neutral wire are covered with black insulations. This is like for the sake of Uganda. And now we want to look at now transmission of electrical energy over long distances. At the generation station, electrical energy is generated at low voltage. Please look at this. Electrical energy is always generated at low voltage. This voltage is stepped up by a step-up transformer at a station for transmission over long distances via transmission cables. So before electricity is transmitted, it has to be stepped up first. The voltage is stepped up to minimize the energy loss, that is I squared RT, in the transmission cables due to their resistance R when current I flows through them for a time t. Yes, you may not have all the details, but all we are saying is that we have to step up that voltage so that we minimize power loss or energy loss, and that is in the form of I squared RT. So once you increase, if you increase the voltage, it means you reduce the current. So when the current reduces, I reduces, that means you're going to minimize the power loss. Thus, the value of I in P is equal to I squared R is minimized when voltage P is equal to IV is stepped up. Now look at this equation. P is equal to IV. P is equal to IV. It's the same power. That means that when you step up, when this one increases, when V increases, I will reduce. And when V reduces, I will increase. So always we step up the voltage. We step up the voltage so that the current is minimum. And once the value of I is minimum, then it means even the power loss is minimum. In the substations, the voltage is stepped down. The substations are the ones like the transformers that supply, where the transformers that supply energy, electricity to the homes, to factories, to schools. Yeah. So in the substations, the voltage is stepped down by a step-down transformer in stages to 240 volts, which is the main voltage at homes, schools, industries, factories, etc. So this is what we are saying. It's generated here. Electricity is generated at the power station and stepped up. There's a step-up transformer. So then we have pylons here, and it's transmitted. So we have a high voltage. The power now, the electricity here is at a high voltage for transmission over very many kilometers. And then at the substation here, it's stepped down. So we have a step-down transformer. It's stepped down, and once it's stepped down, it can be stepped down, and there is current supplied to the heavy industries, and stepped down further to be supplied to the small industries, and stepped down further to be supplied to the homes. Yeah, but basically we just understand that after generation, it's stepped up for transmission and stepped down for consumption. And this is the summary. We are saying the generator at the power station will produce a step-up transformer to step it up so that it is transmitted at a high voltage and low current over long distances on pylons, and then stepped down before reaching the consumer. Let me show you a video to demonstrate that. Note: aluminium cables are used during high voltage transmissions because aluminium has a low density. So if you look at those cables, they are always made up of aluminium. For transmission, they are thick, but they are made up of aluminium. Why? Aluminium has a low density. Hence, the thick cables of aluminium are light enough to be supported on high pylons. Those pylons. Question: explain why voltage is first stepped up before transmission. This is a question that everyone should know. Stepping up the voltage means that there is small current in transmission. This minimizes energy or power loss as heat in the transmission. So advantages of transmitting power at high voltage and low current. Number 1, energy loss as heat in the cable is minimized. Number 2, it reduces the cost of carrying high currents. It reduces the cost of carrying high current because this would require thick wires, very thick wires, so the cost is minimized. So what is the disadvantage of transmitting at high voltages? Number 1, high voltage is dangerous. This is because it ionizes air molecules around the wires, which can cause health hazards like blood cancer to the people. And it is expensive in terms of materials like transformers and high quality wires. By the way, aluminium is not all that cheap. But we are saying it's expensive. You have to have transformers to step up that voltage. You have to, so it makes it expensive. A question: explain how electrical energy is transmitted over long distances. Number 2, state the advantages of transmitting power at high voltages. Those are your own questions. Now, we all know that current is in 2 categories. We have alternating current and we have direct current. I just want to look at something here briefly, although there is an area where we're going to explore this in detail. Advantages of alternating current over direct current. I encourage you to check on YouTube for the video called The Current War. The Current War. War of the Currents. Current War. It was between Tesla and Thomas Edison. Tesla invented the AC, the alternating current, and Thomas Edison, the genius of the Menlo Park, invented the direct current. So they were fighting. There was a very, very big war in America, and you'll find out who won or which current won. So advantages of alternating current over direct current. Alternating current can easily and cheaply be stepped up or stepped down than direct current. Alternating current can easily and cheaply be transmitted over long distances with low power losses. And alternating current can easily be generated compared to direct current. Those are very, very important advantages. Okay. Revision questions. These are just for you. In 2017, number 5, part C of paper 2, there's a question that said, explain why voltage is first stepped up before transmission. And Roman 2, what are the disadvantages of transmitting of transmission at high voltages? And part D of the same question, they said 5 equal electric bulbs are switched on for 8 hours a day for 30 days. If each unit costs shillings 600 and the total monthly bill is 43,200 shillings, find the power rating of each bulb. Ho ho ho, this is a very good one. I encourage you to pause here and first do it. Okay, the solution is here. If you had paused, you must compare with your answer. Number 2, what is meant by the term short circuit? And then part B, we have this number here. Just read through these questions and please do them. Okay, I didn't want to make explanations of this because this is the work we've been doing. These are just examples for you to compare with your solutions that you had about them. Okay, household wiring. Yeah, this should have been at the beginning, but I wanted to bring it at the end. Every circuit is connected in parallel with the power supply in a house, i.e. across the live and the neutral wires. Yeah, this is just for the consumer unit here. You may have the supply cable. This is the neutral, the black, and the live is red. And we have a meter here. So remember, if you remember very well, we said that all fuses, like if you look at fuses and switches, they are connected to the live wire side. This one here, which is brown here, the brown one here, the brown. So where you find a fuse, the fuses are connected to the live wires. Even switches, the same story. And we said these appliances are always connected in. If you have, maybe for example, you have these bulbs, you always connect them across the live wire and the neutral, across the live and the neutral. If you look at this immersion heater, we are connecting across the live and the neutral like that. Yeah, for the cooker, the same story. So you can study this. The earthing is here. This is out of the house. Yeah, just to protect you. You can study this, and in case you have any concern, you can raise it. Yeah, heads but no tails for God and my country. May God bless you.
Everybody's got a story. Everybody's got a song. Everyone's a little different. We've all gone wrong. Then the Savior came and he took the blame, changed everything. Then the Savior came and he took the blame, changed everything. Now I can sing about his forgiveness. I can praise him till the sun goes down. And I can say I am a witness. I was there when his love came down. for my freedom. No more chains on me, 'cause the Savior came and He took the blame, changed everything. Yeah, the Savior came and He took the blame, changed everything.